6.3 Enzyme Kinetics as an approach to understanding mechanism. Biochemists commonly use several approaches to study the mechanism of action of purified enzymes. The three-dimensional structure of the protein provides important information, which is enhanced by classical protein chemistry and modern methods of site-directed mutagenesis, changing the amino acid sequence of a protein by genetic engineering, see Fig. 9-10. These technologies permit enzymologists to examine the role of individual amino acids in enzyme structure and action. However, the oldest approach to understanding enzyme mechanisms, and one that remains very important, is to determine the rate of a reaction, and how it changes in response to changes in experimental parameters, a discipline known as enzyme kinetics. We provide here a basic introduction to the kinetics of enzyme-catalyzed reactions. Substrate concentration affects the rate of enzyme catalyzed reactions. A key factor affecting the rate of a reaction catalyzed by an enzyme is the concentration of substrate S. However, studying the effects of substrate concentration is complicated by the fact that S changes during the course of an in vitro reaction as substrate is converted to product. One simplifying approach in kinetics experiments is to measure the initial rate, or initial velocity, designated V0, Fig. 6-10. In a typical reaction, the enzyme may be present in nanomolar quantities, whereas S may be 5 or 6 orders of magnitude higher. If only the beginning of the reaction is monitored, over a period in which only a small percentage of the available substrate is converted to product, S can be regarded as constant to a reasonable approximation. V0 can then be explored as a function of S, which is adjusted by the investigator. The effect on V0 of varying S when the enzyme concentration is held constant is shown in Figure 6-11. At relatively low concentrations of substrate, V0 increases almost linearly with an increase in S. At higher substrate concentrations, V0 increases by smaller and smaller amounts in response to increases in S. Finally, a point is reached beyond which increases in V0 are vanishingly small as S increases. This plateau-like V0 region is close to the maximum velocity, Vmax. Figure 6-11. The ES complex is the key to understanding this kinetic behavior, just as it was a starting point for our discussion of catalysis. The kinetic pattern in Figure 6-11 led Victor Henry, following Wurtz's lead, to propose in 1903 that the combination of an enzyme with its substrate molecule to form an ES complex is a necessary step in enzymatic catalysis. This idea was expanded into a general theory of enzyme action, particularly by Leonor Michaelis and Michaelis-Menten in 1913. They postulated that the enzyme first combines reversibly with its substrate to form an enzyme-substrate complex in a relatively fast reversible step. The ES complex then breaks down in a slower second step to yield the free enzyme and the reaction product P. Because the slower second reaction, X 6-8, must limit the rate of the overall reaction, the overall rate must be proportional to the concentration of the species that reacts in the second step, that is, ES. Leonor Michaelis, 1875-1949, source, Rockefeller Archive Center. Michaelis-Menten, 1879-1960, source, Courtesy Archives Service Center, University of Pittsburgh. At any given instant in an enzyme-catalyzed reaction, the enzyme exists in two forms, the free or uncombined form E, and the combined form ES. At low S, most of the enzyme is in the uncombined form E. Here, the rate is proportional to S, because the equilibrium of equation 6-7 is pushed toward formation of more ES as S increases. The maximum initial rate of the catalyzed reaction, Vmax, is observed when virtually all the enzyme is present as the ES complex and E is vanishingly small. Under these conditions, the enzyme is saturated with its substrate, so that further increases in S have no effect on rate. This condition exists when S is sufficiently high that essentially all the free enzyme has been converted to the ES form. After the ES complex breaks down to yield the product P, the enzyme is free to catalyze the reaction of another molecule of substrate, and will do so rapidly under saturating conditions. The saturation effect is a distinguishing characteristic of enzymatic catalysts, and is responsible for the plateau observed in Figure 6 to 11, and the pattern seen in the figure is sometimes referred to as saturation kinetics. When the enzyme is first mixed with a large excess of substrate, there is an initial transient period, the pre-steady state, during which the concentration of ES builds up. For most enzymatic reactions, this period is very brief. It is often too short to be easily observed, lasting just microseconds, and is not evident in Figure 6 to 10. We return to the pre-steady state later in this section. The reaction quickly achieves a steady state in which ES and the concentrations of any other intermediates remains approximately constant over time. The concept of a steady state, introduced by G. E. Briggs and Haldane in 1925, is an approximation based on a simple reality. As noted earlier, enzymes are powerful catalysts that are typically present at concentrations orders of magnitude lower than the concentration of substrate. Once the transient phase or pre-steady state has passed, often after only one enzymatic turnover, that is, conversion of one molecule of substrate to one molecule of product on each molecule of enzyme, P is generated at the same rate that S is consumed only if the concentration of the intermediate ES remains steady. The measured V0 generally reflects the steady state, even though V0 is limited to the early part of the reaction. An analysis of these initial rates is referred to as steady-state kinetics. The relationship between substrate concentration and reaction rate can be expressed quantitatively. The curve expressing the relationship between S and V0, Fig. 6 to 11, has the same general shape for most enzymes. It approaches a rectangular hyperbola, which can be expressed algebraically by the Michaelis-Menten equation. Michaelis and Menten derived this equation starting from their basic hypothesis that the rate-limiting step in enzymatic reactions is the breakdown of the ES complex to product and free enzyme. The equation is all these terms, S, V0, Vmax, and a constant, Km, called the Michaelis constant, are readily measured experimentally. Here we develop the basic logic and the algebraic steps in a modern derivation of the Michaelis-Menten equation, which includes the steady-state assumption introduced by Briggs and Haldane. The derivation starts with the two basic steps of the formation and breakdown of ES, ECN 6 to 7 and 6 to 8. Early in the reaction, the concentration of the product, P, is negligible, and we make the simplifying assumption that the reverse reaction, PS, described by K2, can be ignored. This assumption is not critical, but it simplifies our task. The overall reaction then reduces to V0 is determined by the breakdown of ES to form product, which is determined by ES. Because ES in equation 6 to 11 is not easily measured experimentally, we must begin by finding an alternative expression for this term. First, we introduce the term ET, representing the total enzyme concentration, the sum of free and substrate-bound enzyme. Free or unbound enzyme, E, can then be represented by ETES. Also, because S is ordinarily far greater than ET, the amount of substrate bound by the enzyme at any given time is negligible compared with the total S. With these conditions in mind, the following steps lead us to an expression for V0 in terms of easily measurable parameters. Step 1. The rates of formation and breakdown of ES are determined by the steps governed by the rate constants K1, formation, and K1 plus K2, breakdown, to reactants and products, respectively, according to the expressions. Step 2. We now make an important assumption, that the initial rate of reaction reflects a steady state in which ES is constant, that is, the rate of formation of ES is equal to the rate of its breakdown. This is called the steady-state assumption. The expressions in equations 6 to 12 and 6 to 13 can be equated for the steady state, giving Step 3. In a series of algebraic steps, we now solve equation 6 to 14 for ES. First, the left side is multiplied out and the right side simplified to give Adding the term K1, ES, to both sides of the equation and simplifying gives. We then solve this equation for ES. This can now be simplified further, combining the rate constants into one expression. The term K1 plus K2 slash K1 is defined as the Michaelis constant, kilometer substituting. This into equation 6 to 18 simplifies the expression to. Step 4. We can now express V0 in terms of ES. Substituting the right side of equation 6 to 19 for ES in equation 6 to 11 gives. This equation can be further simplified. Because the maximum velocity occurs when the enzyme is saturated, that is, when ES equals ET, Vmax can be defined as K2 ET. Substituting this in equation 6 to 20 gives equation 6 to 9. This is the Michaelis-Menten equation, the rate equation for a one-substrate enzyme-catalyzed reaction. It is a statement of the quantitative relationship between the initial velocity V0, the maximum velocity Vmax, and the initial substrate concentration, S, all related through the Michaelis constant kilometer. Note that Km has units of molar concentration. Does the equation fit experimental observations? Yes, we can confirm this by considering the limiting situations where S is very high or very low, as shown in Figure 6 to 12. Figure 6 to 12. The Michaelis-Menten. An important numerical relationship emerges from the Michaelis-Menten equation in the special case when V0 is exactly 1/2 Vmax, Fig. 6 to 12. Then, on dividing by Vmax, we obtain. Solving for Km, we get Km plus S equals 2S or. This is a very useful, practical definition of Km. Km is equivalent to the substrate concentration at which V0 is 1/2 Vmax. The Michaelis-Menten equation, X 6 to 9, can be algebraically transformed into versions that are useful in the practical determination of Km and Vmax, box 6 to 1, and, as we describe later, in the analysis of inhibitor action, see box 6 to 2. Kinetic parameters are used to compare enzyme activities. It is important to distinguish between the Michaelis-Menten equation and the specific kinetic mechanism on which it was originally based. The equation describes the kinetic behavior of a great many enzymes, and all enzymes that exhibit a hyperbolic dependence of V0 on S are said to follow Michaelis-Menten kinetics. The practical rule that Km equals S when V0 equals 1/2 Vmax, X 623, holds for all enzymes that follow Michaelis-Menten kinetics. The most important exceptions to Michaelis-Menten kinetics are the regulatory enzymes, discussed in section 6.5. However, the Michaelis-Menten equation does not depend on the relatively simple two-step reaction mechanism proposed by Michaelis and Menten, X 6 to 10. Many enzymes that follow Michaelis-Menten kinetics have quite different reaction mechanisms, and enzymes that catalyze reactions with 6 or 8 identifiable steps often exhibit the same steady-state kinetic behavior. Even though equation 6 to 23 holds true for many enzymes, both the magnitude and the real meaning of Vmax and Km can differ from one enzyme to the next. This is an important limitation of the steady-state approach to enzyme kinetics. The parameters Vmax and Km can be obtained experimentally for any given enzyme, but by themselves they provide little information about the number, rates, or chemical nature of discrete steps in the reaction. Steady-state kinetics, nevertheless, is the standard language through which biochemists compare and characterize the catalytic efficiencies of enzymes. Interpreting Vmax and Km. Figure 6 to 12 shows a simple graphical method for obtaining an approximate value for kilometer. A more convenient procedure, using a double reciprocal plot, is presented in box 6 to 1. The Km can vary greatly from enzyme to enzyme, and even for different substrates of the same enzyme, table 6 to 6. The term is sometimes used, often inappropriately, as an indicator of the affinity of an enzyme for its substrate. The actual meaning of Km depends on specific aspects of the reaction mechanism, such as the number and relative rates of the individual steps. For reactions with 2 steps, box 6 to 1 transformations of the Michaelis-Menten equation, the double reciprocal plot. The Michaelis-Menten equation can be algebraically transformed into equations that are more useful in plotting experimental data. One common transformation is derived simply by taking the reciprocal of both sides of the Michaelis-Menten equation, separating the components of the numerator on the right side of the equation gives, which simplifies to. This form of the Michaelis-Menten equation is called the Lineweaver-Burke equation. For enzymes obeying the Michaelis-Menten relationship, a plot of 1/V0 versus 1/S, the double reciprocal of the V0 versus S plot we have been using to this point, yields a straight line, Fig. 1. This line has a slope of km/Vmax, an intercept of 1/Vmax on the 1/V0 axis, and an intercept of 1/km on the 1/S axis. The double reciprocal presentation, also called a Lineweaver-Burke plot, has the great advantage of allowing a more accurate determination of Vmax, which can only be approximated from a simple plot of V0 versus S. See Fig. 6-12. Other transformations of the Michaelis-Menten equation have been derived, each with some particular advantage in analyzing enzyme kinetic data. See problem 16 at the end of this chapter. The double reciprocal plot of enzyme reaction rates is very useful in distinguishing between certain types of enzymatic reaction mechanisms. See Fig. 6-14, and in analyzing enzyme inhibition, see box 6-2. Figure 1a double reciprocal, or Lineweaver. Table 6-6 enzymes hexokine 0 carbonic chyme beta-galactose 3 when K2 is rate limiting, K2 K1, and Km reduces to K1/K1, which is defined as the dissociation constant, Kd, of the ES complex. Where these conditions hold, Km does represent a measure of the affinity of the enzyme for its substrate in the ES complex. However, this scenario does not apply for most enzymes. Sometimes K2 K1, and then Km equals K2/K1. In other cases, K2 and K1 are comparable, and Km remains a more complex function of all three rate constants, ECN 6-24. The Michaelis-Menten equation and the characteristic saturation behavior of the enzyme still apply, but Km cannot be considered a simple measure of substrate affinity. Even more common are cases in which the reaction goes through several steps after formation of ES. Km can then become a very complex function of many rate constants. The quantity Vmax also varies greatly from one enzyme to the next. If an enzyme reacts by the two-step Michaelis-Menten mechanism, Vmax equals K2 ET, where K2 is rate limiting. However, the number of reaction steps and the identity of the rate limiting steps can vary from enzyme to enzyme. For example, consider the common situation where product release, EPE plus P, is rate limiting. Early in the reaction, when P is low, the overall reaction can be adequately described by the scheme. Table 6. Some enzymes catalase H, carbonic, acetyl, beta-lactam, fumarate, RECA protein. In this case, most of the enzyme is in the EP form at saturation, and Vmax equals K3 ET. It is useful to define a more general rate constant, Cat, to describe the limiting rate of any enzyme-catalyzed reaction at saturation. If the reaction has several steps and one is clearly rate limiting, Cat is equivalent to the rate constant for that limiting step. For the simple reaction of equation 6-10, Cat equals K2. For the reaction of equation 6-25, when product release is clearly rate limiting, Cat equals K3. When several steps are partially rate limiting, Cat can become a complex function of several of the rate constants that define each individual reaction step. In the Michaelis-Menten equation, Cat equals Vmax/ET. And equation 6-9 becomes the constant Cat is a first-order rate constant and hence has units of reciprocal time. It is also called the turnover number. It is equivalent to the number of substrate molecules converted to product in a given unit of time on a single enzyme molecule when the enzyme is saturated with substrate. The turnover numbers of several enzymes are given in Table 6-7. Comparing catalytic mechanisms and efficiencies. The kinetic parameters Cat and Km are useful for the study and comparison of different enzymes, whether their reaction mechanisms are simple or complex. Each enzyme has values of Cat and Km that reflect the cellular environment, the concentration of substrate normally encountered in vivo by the enzyme, and the chemistry of the reaction being catalyzed. The parameters Cat and Km also allow us to evaluate the kinetic efficiency of enzymes, but either parameter alone is insufficient for this task. Two enzymes catalyzing different reactions may have the same Cat turnover number, yet the rates of the uncatalyzed reactions may be different, and thus the rate enhancements brought about by the enzymes may differ greatly. Experimentally, the Km for an enzyme tends to be similar to the cellular concentration of its substrate. An enzyme that acts on a substrate present at a very low concentration in the cell usually has a lower Km than an enzyme that acts on a substrate that is more abundant. The best way to compare the catalytic efficiencies of different enzymes, or the turnover of different substrates by the same enzyme, is to compare the ratio Cat/Km for the two reactions. This parameter, sometimes called the specificity constant, is the rate constant for the conversion of E plus S to E plus P. When S/Km, equation 6-26 reduces to the form V0. In this case depends on the concentration of two reactants, ET and S. So this is a second-order rate equation, and the constant Cat/Km is a second-order rate constant with units of m1s1. There is an upper limit to Cat/Km imposed by the rate at which E and S can diffuse together in an aqueous solution. This diffusion-controlled limit is 10^8 to 10^9 m1s1, and many enzymes have a Cat/Km near this range, table 6-8. Such enzymes are said to have achieved catalytic perfection. Note that different values of Cat and Km can produce the maximum ratio. Table 6. Close to the limit, enzyme Cat/acetyl 9 times carbonic times 10 to 1. Catalase 1.1 crotonase 2 times 10 fumarate 5 times 1. Beta-lac 2 times source. Worked example. An enzyme a T mu ms solution 6 to equation allows us to, once you have Cat thus simplify worked example in a set V0 solution. Many enzymes catalyze reactions with two or more substrates. We have seen how S affects the rate of a simple enzymatic reaction with only one substrate molecule, Sp. In most enzymatic reactions, however, two, and sometimes more, different substrate molecules bind to the enzyme and participate in the reaction. Nearly 2/3 of all enzymatic reactions have two substrates and two products. These are generally reactions in which a group is transferred from one substrate to the other, or one substrate is oxidized while the other is reduced. For example, in the reaction catalyzed by hexokinase, ATP and glucose are the substrate molecules and ADP and glucose 6-phosphate are the products. A phosphoryl group is transferred from ATP to glucose. The rates of such bisubstrate reactions can also be analyzed by the Michaelis-Menten approach. Hexokinase has a characteristic Km for each of its substrates, table 6-6. Enzymatic reactions with two substrates proceed by one of several different types of pathways. In some cases, both substrates are bound to the enzyme concurrently at some point in the course of the reaction, forming a non-covalent ternary complex, Fig. 6-13a. The substrates bind in a random sequence or in a specific order. In other cases, the first substrate is converted to product and dissociates before the second substrate binds, so no ternary complex is formed. An example of this is the ping-pong, or double displacement, mechanism, Fig. 6-13b. A shorthand notation developed by W. Cleland can be helpful in describing reactions with multiple substrates and products. In this system, referred to as Cleland nomenclature, substrates are denoted A, B, C, and D in the order in which they bind to the enzyme, and products are denoted P, Q, S, T in the order in which they dissociate. Enzymatic reactions with 1, 2, 3, or 4 substrates are referred to as uni, bi, ter, and quad, respectively. The enzyme is, as usual, denoted E, but if it is modified in the course of the reaction, successive forms are denoted F, G, and so on. The progress of the reaction is indicated with a horizontal line, with successive chemical species indicated below it. If there is an alternative in the reaction path, the horizontal line is bifurcated. Steps involving binding and dissociating substrates and products are indicated with vertical lines. Common reactions with 2 substrates and 2 products, bi, are described with the shorthand forms illustrated in Figure 16-13C for an ordered bi reaction and a random bi reaction. In the latter example, the release of product is also random, as indicated by the 2 sets of bifurcations. Rarely, the binding of substrates is ordered and release of products random, or vice versa, eliminating the bifurcation at one end or the other of the progress line. In a ping-pong reaction, lacking a ternary complex, the pathway has a transient second form of the enzyme, F, Fig. 6-13d. This is the form in which a group has been transferred from the first substrate, A, to create a transient covalent attachment to the enzyme. As noted above, such reactions are often called double displacement reactions, as a group is transferred first from substrate A to the enzyme, and then from the enzyme to substrate B. Substrates A and B do not encounter each other on the enzyme. Figure 6-13 Common mechanisms for enzyme-catalyzed bisubstrate reactions. A. The enzyme and both substrates come together to form a ternary complex. In ordered binding, substrate 1 must bind before substrate 2 can bind productively. In random binding, the substrates can bind in either order. B. An enzyme substrate complex forms, a product leaves. Michaelis-Menten steady-state kinetics can provide only limited information about the number of steps and intermediates in an enzymatic reaction, but it can be used to distinguish between pathways that have a ternary intermediate and pathways including ping-pong pathways that do not, Fig. 6-14. As we will see when we consider enzyme inhibition, steady-state kinetics can also distinguish between ordered and random binding of substrates and products in reactions with ternary intermediates. Figure 6-14 Steady-state kinetic analysis of bisubstrate reactions. In these double reciprocal plots, see box 6-1, the concentration of substrate 1 is varied while the concentration of substrate 2 is held constant. This is repeated for several values of S2. Enzyme activity depends on pH. In general, steady-state kinetics provides information required to characterize an enzyme and assess its catalytic efficiency. Additional information can be gained by examining how the key experimental parameters Cat and Cat/Km change when reaction conditions change, particularly pH. Enzymes have an optimum pH or pH range at which their activity is maximal Fig. 6-15. At higher or lower pH, activity decreases. This is not surprising. Amino acid side chains in the active site may act as weak acids and bases only if they maintain a certain state of ionization. Elsewhere in the protein, removing a proton from a His residue, for example, might eliminate an ionic interaction essential for stabilizing the active conformation of the enzyme. A less common cause of pH sensitivity is titration of a group on the substrate. Figure 6. The pH range over which an enzyme undergoes changes in activity can provide a clue to the type of amino acid residue involved, see Table 3-1. A change in activity near pH 7.0, for example, often reflects titration of a His residue. The effects of pH must be interpreted with some caution, however. In the closely packed environment of a protein, the pKa of amino acid side chains can be significantly altered. For example, a nearby positive charge can lower the pKa of a Lis residue, and a nearby negative charge can increase it. Such effects sometimes result in a pKa that is shifted by several pH units from its value in the free amino acid. In the enzyme acetoacetate decarboxylase, for example, one Lis residue has a pKa of 6.6, compared with 10.5 in free lysine, due to electrostatic effects of nearby positive charges. Pre-steady-state kinetics can provide evidence for specific reaction steps. The mechanistic insight provided by steady-state kinetics can be augmented, sometimes dramatically, by an examination of the pre-steady state. Consider an enzyme with a reaction mechanism that conforms to the scheme in equation 6 to 25, featuring 3 steps. Overall catalytic efficiency for this reaction can be assessed with steady-state kinetics, but the rates of the individual steps cannot be determined in this way, and the slow, rate-limiting step can rarely be identified. To measure the rate constants of individual steps, the reaction must be studied during its pre-steady state. The first turnover of an enzyme-catalyzed reaction often occurs in seconds or milliseconds, so researchers use special equipment that allows mixing and sampling on this timescale, Fig. 6-16a. Reactions are stopped and protein-bound products are quantified, after the timed addition and rapid mixing of an acid that denatures the protein and releases all bound molecules. A detailed description of pre-steady-state kinetics is beyond the scope of this text, but we can illustrate the power of this approach by a simple example of an enzyme that uses the pathway shown in equation 6 to 25. This example also involves an enzyme that catalyzes a relatively slow reaction, so the pre-steady state is more conveniently observed. For many enzymes, dissociation of product is rate-limiting. In this example, Fig. 6-16b, c, the rate of dissociation of the product, K3, is slower than the rate of its formation, K2. Product dissociation therefore dictates the rates observed in the steady state. How do we know that K3 is rate-limiting? A slow K3 gives rise to a burst of product formation in the pre-steady state, because the preceding steps are relatively fast. The burst reflects the rapid conversion of one molecule of substrate to one molecule of product at each enzyme active site. The observed rate of product formation slows to the steady-state rate as the bound product is slowly released. Each enzymatic turnover after the first one must proceed through the slow product release step. However, the rapid generation of product in that first turnover provides much information. The amplitude of the burst when one molecule of product is generated per molecule of enzyme present, Fig. 6-16c, measured by extrapolating the steady-state progress line back to zero time is the highest amplitude possible. This provides one piece of evidence that product release is, indeed, rate-limiting. The rate constant for the chemical reaction step, K2, can be derived from the observed rate of the burst phase. Of course, enzymes do not always conform to the simple reaction scheme of equation 625. Formally, the observation of a burst indicates that a rate-limiting step, typically, product release, or an enzyme conformational change, or another chemical step, occurs after formation of the product being monitored. Additional experiments and analysis can often define the rates of each step in a multi-step enzymatic reaction. Some examples of the application of pre-steady-state kinetics are included in the descriptions of specific enzymes in section 6.4. Enzymes are subject to reversible or irreversible inhibition. Enzyme inhibitors are molecules that interfere with catalysis, slowing or halting enzymatic reactions. Enzymes catalyze virtually all cellular processes, so it should not be surprising that enzyme inhibitors are among the most important pharmaceutical agents known. For example, aspirin, acetylsalicylate, inhibits the enzyme that catalyzes the first step in the synthesis of prostaglandins, compounds involved in many processes, including some that produce pain. The study of enzyme inhibitors also has provided valuable information about enzyme mechanisms and has helped define some metabolic pathways. There are two broad classes of enzyme inhibitors, reversible and irreversible. Figure 6-16 pre-steady-state kinetics. Reversible inhibition. One common type of reversible inhibition is called competitive, Fig. 6-17a. A competitive inhibitor competes with the substrate for the active site of an enzyme. While the inhibitor, I, occupies the active site, it prevents the substrate from binding to the enzyme. Many competitive inhibitors are structurally similar to the substrate and combine with the enzyme to form an EI complex, but without leading to catalysis. Even fleeting combinations of this type will reduce the efficiency of an enzyme. By taking into account the molecular geometry of inhibitors, we can reach conclusions about which parts of the normal substrate bind to the enzyme. Competitive inhibition can be analyzed quantitatively by steady-state kinetics. In the presence of a competitive inhibitor, the Michaelis-Menten equation, ECN 6-9, becomes where equation 6-28 describes the important features of competitive inhibition. The experimentally determined variable alpha Km, the Km observed in the presence of the inhibitor, is often called the apparent kilometer. Bound inhibitor does not inactivate the enzyme. When the inhibitor dissociates, substrate can bind and react. Because the inhibitor binds reversibly to the enzyme, the competition can be biased to favor the substrate simply by adding more substrate. When S far exceeds I, the probability that an inhibitor molecule will bind to the enzyme is minimized, and the reaction exhibits a normal Vmax. However, in the presence of inhibitor, higher concentrations of substrate are needed to approach that Vmax. The S at which V0 equals 1/2 Vmax, the apparent Km, increases in the presence of inhibitor by the factor A. This effect on apparent Km, combined with the absence of an effect on Vmax, is diagnostic of competitive inhibition, and is readily revealed in a double reciprocal plot, box 6-2. The equilibrium constant for inhibitor binding, Ki, can be obtained from the same plot. Figure 6-17. 3 types of reversible inhibition. A medical therapy based on competition at the active site is used to treat patients who have ingested methanol, a solvent found in gasoline antifreeze. The liver enzyme alcohol dehydrogenase converts methanol to formaldehyde, which is damaging to many tissues. Blindness is a common result of methanol ingestion, because the eyes are particularly sensitive to formaldehyde. Ethanol competes effectively with methanol as an alternative substrate for alcohol dehydrogenase. The effect of ethanol is much like that of a competitive inhibitor, with the distinction that ethanol is also a substrate for alcohol dehydrogenase, and its concentration will decrease over time as the enzyme converts it to acetaldehyde. The therapy for methanol poisoning is slow intravenous infusion of ethanol, at a rate that maintains a controlled concentration in the blood for several hours. This slows the formation of formaldehyde, lessening the danger, while the kidneys filter out the methanol to be excreted harmlessly in the urine. 2 other types of reversible inhibition, uncompetitive and mixed, can be defined in terms of one substrate enzymes, but in practice are observed only with enzymes having 2 or more substrates. An uncompetitive inhibitor, Fig. 6-17b, binds at a site distinct from the substrate active site and, unlike a competitive inhibitor, binds only to the ES complex. In the presence of an uncompetitive inhibitor, the Michaelis-Menten equation is altered to where, as described by equation 6-29, at high concentrations of substrate, V0 approaches Vmax/alpha. Thus, an uncompetitive inhibitor lowers the measured Vmax. Apparent Km also decreases because the S required to reach 1/2 Vmax decreases by the factor alpha. This behavior can be explained as follows. Because the enzyme is inactive when the uncompetitive inhibitor is bound, but the inhibitor is not competing with substrate for binding, the inhibitor effectively removes some fraction of the enzyme molecules from the reaction. Given that Vmax depends on E, the observed Vmax decreases, and given that inhibitor binds only to the ES complex, only ES, not free enzyme, is deleted from the reaction, so that S, needed to reach 1/2 Vmax, that is, Km declines by the same amount. A mixed inhibitor, Fig. 6-17c, also binds at a site distinct from the substrate active site, but it binds to either E or ES. The rate equation describing mixed inhibition is where alpha and alpha are defined as above. A mixed inhibitor usually affects both Km and Vmax. Vmax is affected because the inhibitor renders some fraction of the available enzyme molecules inactive, lowering the effective E on which Vmax depends. The Km may increase or decrease depending on which enzyme form, E or Es, the inhibitor binds to most strongly. The special case of alpha equals alpha, rarely encountered in experiments, classically has been defined as non-competitive inhibition. Examine equation 6 to 30 to see why a non-competitive inhibitor would affect the Vmax, but not the kilometer. Box 6 to 2 kinetic tests for determining inhibition. Mechanisms. The double reciprocal plot, see box 6 to 1, offers an easy way of determining whether an enzyme inhibitor is competitive, uncompetitive, or mixed. Two sets of rate experiments are carried out, with the enzyme concentration held constant in each set. In the first set, S is also held constant, permitting measurement of the effect of increasing inhibitor concentration, I on the initial rate V0, not shown. In the second set, I is held constant but S is varied. The results are plotted as 1/V0 versus 1/S. Figure 1 shows a set of double reciprocal plots, one obtained in the absence of inhibitor and two at different concentrations of a competitive inhibitor. Increasing I results in a family of lines with a common intercept on the 1/V0 axis, but with different slopes. Because the intercept on the 1/V0 axis equals 1/Vmax, we know that Vmax is unchanged by the presence of a competitive inhibitor. That is, regardless of the concentration of a competitive inhibitor, a sufficiently high substrate concentration will always displace the inhibitor from the enzyme's active site. Above the graph is the rearrangement of equation 6 to 28 on which the plot is based. The value of A can be calculated from the change in slope at any given I. Knowing I and alpha, we can calculate Ki from the expression. For uncompetitive and mixed inhibition, similar plots of rate data give the families of lines shown in figures 2 and 3. Changes in axis intercepts signal changes in Vmax and kilometer. Figure 1 competitive. Figure 2 uncompetitive. Figure 3 mixed inhibition. Equation 6 to 30 is a general expression for the effects of reversible inhibitors, simplifying to the expressions for competitive and uncompetitive inhibition when alpha equals 1.0 or alpha equals 1.0, respectively. From this expression we can summarize the effects of inhibitors on individual kinetic parameters. For all reversible inhibitors, the apparent Vmax equals Vmax/alpha, because the right side of equation 6 to 30 always simplifies to Vmax/alpha at sufficiently high substrate concentrations. For competitive inhibitors, alpha equals 1.0 and can thus be ignored. Taking this expression for apparent Vmax, we can also derive a general expression for apparent Km to show how this parameter changes in the presence of reversible inhibitors. Apparent Km, as always, equals the S, at which V0 is 1/2 apparent Vmax or, more generally, when V0 equals Vmax/2 alpha. This condition is met when S equals alpha Km/alpha. Thus, apparent Km equals alpha Km/alpha. The terms alpha and alpha reflect the binding of inhibitor to E and Es, respectively. Thus, the term alpha Km/alpha is a mathematical expression of the relative affinity of inhibitor for the two enzyme forms. This expression is simpler when either alpha or alpha is 1.0 for uncompetitive or competitive inhibitors, as summarized in Table 6 to 9. Table 6 to 9 effects of reversible inhibitors on apparent Vmax and apparent Km. Inhibitor type apparent mixed Vmax. In practice, uncompetitive and mixed inhibition are observed only for enzymes with two or more substrates, say, S1 and S2, and are very important in the experimental analysis of such enzymes. If an inhibitor binds to the site normally occupied by S1, it may act as a competitive inhibitor in experiments in which S1 is varied. If an inhibitor binds to the site normally occupied by S2, it may act as a mixed or uncompetitive inhibitor of S1. The actual inhibition patterns observed depend on whether the S1 and S2 binding events are ordered or random, and thus the order in which substrates bind and products leave the active site can be determined. Product inhibition experiments in which one of the reaction products is provided as an inhibitor are often particularly informative. If only one of two reaction products is present, no reverse reaction can take place. However, a product generally binds to some part of the active site and can thus serve as an effective inhibitor when the second product is not present. Enzymologists can combine steady-state kinetic studies involving different combinations and amounts of products and inhibitors with pre-steady-state analysis to develop a detailed picture of the mechanism of a bisubstrate reaction. Worked example: Km. The researchers a factor solution competitive inhibitor is defined. Irreversible inhibition. The irreversible inhibitors bind covalently with or destroy a functional group on an enzyme that is essential for the enzyme's activity, or they form a highly stable non-covalent association. Formation of a covalent link between an irreversible inhibitor and an enzyme is a particularly effective way to inactivate an enzyme. Irreversible inhibitors are another useful tool for studying reaction mechanisms. Amino acids with key catalytic functions in the active site can sometimes be identified by determining which residue is covalently linked to an inhibitor after the enzyme is inactivated. An example is shown in Figure 6-18. A special class of irreversible inhibitors is the suicide inactivators. These compounds are relatively unreactive until they bind to the active site of a specific enzyme. A suicide inactivator undergoes the first few chemical steps of the normal enzymatic reaction, but instead of being transformed into the normal product, the inactivator is converted to a very reactive compound that combines irreversibly with the enzyme. These compounds are also called mechanism-based inactivators, because they hijack the normal enzyme reaction mechanism to inactivate the enzyme. Suicide inactivators play a significant role in rational drug design, a modern approach to obtaining new pharmaceutical agents in which chemists synthesize novel substrates based on knowledge of substrates and reaction mechanisms. A well-designed suicide inactivator is specific for a single enzyme and is unreactive until it is within that enzyme's active site, so drugs based on this approach can offer the important advantage of few side effects. Box 6-3. Some additional examples of irreversible inhibitors of medical importance are described in section 6.4. Figure 6-18. Irreversible inhibition. Reaction of chymotrypsin with diisopropyl fluorophosphate, DIFP, which modifies SER195, irreversibly inhibits the enzyme. This has led to the conclusion that SER195 is the key active site SER residue in chymotrypsin. An irreversible inhibitor need not bind covalently to the enzyme. Non-covalent binding is enough, if that binding is so tight that the inhibitor dissociates only rarely. How does a chemist develop a tight binding inhibitor? Recall that enzymes evolve to bind most tightly to the transition states of the reactions that they catalyze. In principle, if one can design a molecule that looks like that reaction transition state, it should bind tightly to the enzyme. Even though transition states cannot be observed directly, chemists can often predict the approximate structure of a transition state based on accumulated knowledge about reaction mechanisms. Although the transition state is by definition transient and thus unstable, in some cases, stable molecules can be designed that resemble transition states. These are called transition state analogues. They bind to an enzyme more tightly than does the substrate in the ES complex, because they fit into the active site better, that is, form a greater number of weak interactions than the substrate itself. The idea of transition state analogues was suggested by Pong in the 1940s, and it has been explored using a variety of enzymes. For example, transition state analogues designed to inhibit the glycolytic enzyme aldolase bind to that enzyme more than 4 orders of magnitude more tightly than do its substrates. Fig. 6-19. A transition state analog cannot perfectly mimic a transition state. Some analogues, however, bind to a target enzyme 10^2 to 10^8 times more tightly than does the normal substrate, providing good evidence that enzyme active sites are indeed complementary to transition states. The concept of transition state analogues is important to the design of new pharmaceutical agents. As we shall see in section 6.4, the powerful anti-HIV drugs called protease inhibitors were designed in part as tight-binding transition state analogues. Box 6-3 Medicine curing African sleeping sickness with a biochemical Trojan horse. African sleeping sickness or African trypanosomiasis is caused by protists, single-celled eukaryotes, called trypanosomes, Fig. 1. This disease and related trypanosome-caused diseases is medically and economically significant in many developing nations. Until the late 20th century, the disease was virtually incurable. Vaccines are ineffective because the parasite has a novel mechanism to evade the host immune system. The cell coat of trypanosomes is covered with a single protein, which is the antigen to which the human immune system responds. Every so often, however, by a process of genetic recombination, see Table 28:1, a few cells in the population of infecting trypanosomes switch to a new protein coat, not recognized by the immune system. This process of changing coats can occur hundreds of times. The result is a chronic cyclic infection. The human host develops a fever, which subsides as the immune system beats back the first infection. Trypanosomes with changed coats then become the seed for a second infection, and the fever recurs. This cycle can repeat for weeks, and the weakened person eventually dies. Some modern approaches to treating African sleeping sickness have been based on an understanding of enzymology and metabolism. In at least one such approach, this involves pharmaceutical agents designed as mechanism-based enzyme inactivators, suicide inactivators. A vulnerable point in trypanosome metabolism is the pathway of polyamine biosynthesis. The polyamine spermine and spermidine, involved in DNA packaging, are required in large amounts in rapidly dividing cells. The first step in their synthesis is catalyzed by ornithine decarboxylase, an enzyme that requires for its function a coenzyme called pyridoxal phosphate. Pyridoxal phosphate, PLP, derived from vitamin B6, forms a covalent bond with the amino acid substrates of the reactions it is involved in and acts as an electron sink to facilitate a variety of reactions, see Fig. 22-32. In mammalian cells, ornithine decarboxylase undergoes rapid turnover, that is, a rapid, constant round of enzyme degradation and synthesis. In some trypanosomes, however, the enzyme, for reasons not well understood, is stable, not readily replaced by newly synthesized enzyme. An inhibitor of ornithine decarboxylase that binds permanently to the enzyme would thus have little effect on human cells, which could rapidly replace inactivated enzyme, but would adversely affect the parasite. Figure 1 Trypanosoma brucei rhodesians, one of several trypanosomes known to cause African sleeping sickness. Source: John Mansfield, University of Wisconsin-Madison, Department of Bacteriology. Figure 2 Mechanism of ornithine decarboxylase reaction. The first few steps of the normal reaction catalyzed by ornithine decarboxylase are shown in Figure 2. Once CO2 is released, the electron movement is reversed and putrescine is produced, see Fig. 22-32. Based on this mechanism, several suicide inactivators have been designed, one of which is difluoromethylornithine, Dfmo. Dfmo is relatively inert in solution. When it binds to ornithine decarboxylase, however, the enzyme is quickly inactivated, Fig. 3. The inhibitor acts by providing an alternative electron sink in the form of two strategically placed fluorine atoms, which are excellent leaving groups. Instead of electrons moving into the ring structure of PLP, the reaction results in displacement of a fluorine atom. The S of a cis residue at the enzyme's active site then forms a covalent complex with the highly reactive PLP inhibitor adduct, in an essentially irreversible reaction. In this way, the inhibitor makes use of the enzyme's own reaction mechanisms to kill it. Figure 3 Inhibition of ornithine decarboxylase by Dfmo. Dfmo has proved highly effective against African sleeping sickness in clinical trials, and is now used to treat African sleeping sickness caused by Trypanosoma brucei gambiens. Approaches such as this show great promise for treating a wide range of diseases. The design of drugs based on enzyme mechanism and structure can complement the more traditional trial and error methods of developing pharmaceuticals. Summary 6.3 Enzyme Kinetics as an approach. To understanding mechanism. Most enzymes have certain kinetic properties in common. When substrate is added to an enzyme, the reaction rapidly achieves a steady state in which the rate at which the ES complex forms balances the rate at which it breaks down. As S increases, the steady-state activity of a fixed concentration of enzyme increases in a hyperbolic fashion to approach a characteristic maximum rate, Vmax, at which essentially all the enzyme has formed a complex with substrate. The substrate concentration that results in a reaction rate equal to 1/2 Vmax is the Michaelis constant Km, which is characteristic for each enzyme acting on a given substrate. The Michaelis-Menten equation relates initial velocity to S and Vmax through the constant kilometer. Michaelis-Menten kinetics is also called steady-state kinetics. Km and Vmax have different meanings for different enzymes. The limiting rate of an enzyme-catalyzed reaction at saturation is described by the constant Cat, the turnover number. The ratio Cat/Km provides a good measure of catalytic efficiency. The Michaelis-Menten equation is also applicable to bisubstrate reactions, which occur by ternary complex or ping-pong, double displacement pathways. Figure 6-19 structure of the aldolase found in bisphosphate. Every enzyme has an optimum pH or pH range at which it has maximal activity. Pre-steady-state kinetics can provide added insight into enzymatic reaction mechanisms. Reversible inhibition of an enzyme may be competitive, uncompetitive, or mixed. Competitive inhibitors compete with substrate by binding reversibly to the active site, but they are not transformed by the enzyme. Uncompetitive inhibitors bind only to the ES complex, at a site distinct from the active site. Mixed inhibitors bind to either E or ES, again at a site distinct from the active site. In irreversible inhibition, an inhibitor binds permanently to an active site by forming a covalent bond or a very stable non-covalent interaction. 6.4